Uh, Dear friends, welcome to the 15th Differential Geometry video course. I'll start by reminding you the lemma proved by Hilbert. We stated and proved this last time, but since we will make use of it, I'll just restate it and remind you. So let M be a point of a surface M in R3 such that the following conditions hold. First one is that the first principal curvature, the larger one, has a local maximum at the point M. The second condition is that the smaller principal curvature K2 has a local minimum at M, and K1M is larger than K2M. K1 is larger than or equal to K2 always by the choice, but this time we want strict inequality. Then the conclusion is that then the Gaussian curvature at M is non-positive. So that was the content of Hilbert's lemma. We proved this last time. Today I'll use it to prove the following theorem, so-called Liebman's theorem. So theorem due to Liebman. This is a characterization of sphere in geometrical terms. So if M is a compact surface with constant Gaussian curvature K, then M is a sphere of radius 1 over square root of K. Well, since M is a compact surface, there is at least one point at which the Gaussian curvature is positive, but since by assumption the Gaussian curvature is constant, K is necessarily a positive number. That's why we can take square root of it and divide by, the square root of K. So K is positive since K is compact. Okay, we know this. That was another theorem we proved. All right, now let's see the proof of this theorem. Okay, well, since M is a surface in R3, is a compact surface. M is orientable. Okay, this is a fact which cannot be proved, can't be proved by the tools of this course. We need intersection theory or characteristic classes. So this is a fact which we will borrow from algebraic topology basically. Here I just want to emphasize that the assumption of being compact is essential here, because you know that Klein but sorry Möbius band is a uh, is a well, you can think of this as an open manifold by just deleting its boundary. So this is non-orientable, and well, it is either non-compact or compact with boundary. But this is not a compact, closed surface in R3. So to avoid such, possibilities, uh, uh, it is necessary to assume that M is compact. If M is a compact surface without boundary in R3, then it is necessarily orientable. Okay. All right. So this is a topological fact. All right. Since it is orientable, so we have uh, smooth varying, smooth unit normal vector field defined on all of M. Okay. Therefore, principal curvature functions are globally defined on M, uh, and K1, uh, which is larger than K2, are zero at all points. Why is that? Because at some point, you know, either K1 or one of them is positive, but we know that Gaussian curvature is positive, therefore both of them are positive. Why one of them is positive at some point? The reason is that, since M is a compact surface, there is a point at which the Gaussian curvature is positive, but at that point, actually, both of them, both K1 and K2 are positive. Okay. Well, in particular, these are continuous functions on a compact set, therefore they have maximums and minimums. In particular, K1 has a maximum value at some point, say P. Okay, so K1 of P is larger than or equal to K1 of any other point. Okay. However, uh, K, which is Gaussian curvature, which is K1 and K2, is constant, and thus uh, K2 has a minimum value at P. Has its minimum value at P. Why is it? Because the product is constant. So if this number achieves its maximum, then the second number should achieve its minimum at that point. Therefore, we have this conclusion. Okay. Well, if K1P is strictly larger than K2P at this point, then by the above lemma, Hilbert's lemma, by Hilbert's lemma, which says that if K1 has a maximum at a point, and if K2 has minimum at the same point, and if at that point K1 is strictly larger than K2, then Gaussian curvature is necessarily negative, non-positive. Then by Hilbert's lemma, Kt should be non-positive, which is a contradiction. Uh, since K is positive, and Gaussian curvature is a constant function. Okay. Well, so K1P must be equal to K2P because K1P is greater than or equal to K2, and it is not strictly larger than K2. Therefore, they must be equal. But this means what? The maximum value of the smaller function is equal to the minimum value of the smaller function. This is possible only if these functions are equal to each other at all points. So K1 Q equals K2 Q at all Q in M. Okay. Well, this means that hence M is an all umbilic surface. Therefore, it is either a part of a sphere or a part of a plane. Since the curvature is positive, Gaussian curvature, it should be a part of a sphere. Hence, it follows that M a is a part of a sphere of radius 1 over square root of the Gaussian curvature. However, M is a compact surface without boundary, and it's a subset of a sphere, which is also compact. Therefore, M should be equal to the surface. Uh, by compactness and connectedness of M, M is equal to the sphere. Well, the reason is actually simple. M is a surface which lies inside a sphere. M is since it is compact, it's a closed subset of the sphere, but M is also a surface. Therefore, it's an open subset of the sphere because at each point of M you can find an open set which lies inside M. Therefore, which lies inside S2. So M is both a closed and open subset of the sphere, but since sphere is also connected, M should be uh, M should be equal to the sphere. By compactness of S2 and connectedness Okay, compactness of M and connectedness of the sphere. Okay, so this finishes the proof. Okay, let's see. Well, we will start a new section, section 6.4, called Isometries and Local Isometries. Okay. Okay. All right. Well, we start with the definition. If so, okay. Definition. If P and Q are points of M in R3, the intrinsic distance from P to Q is defined to be the infimum of lengths L alpha of all curves alpha from P to Q. Okay. This distance, it is denoted as rho PQ. Okay. Well, what is this intrinsic distance? Actually, it is something we use every day in in daily life. Why is that? Well, the world we are living, although some people do not believe it, it is a sphere, right? It's round. And how do you measure distances on the sphere? Well, suppose you are at this point, and this is another point, P to Q. You look at all the paths joining these two and take the minimum. Well, it will be uh, a geodesic, and geodesic is a great circle. So this is a great circle, okay, joining these 2 points. And the distance is this, is the length of this curve. However, the Euclidean distance between these 2 points is, of course, the length of the line segment joining P to Q. But on Earth, we cannot just go through along this blue path, because you have to dig inside the Earth and go, beneath surface. This is not what we do. Usually, we just, follow geodesics. So intrinsic distance is something actually we are familiar with. It is the distance given by, you know, paths joining P to Q. You just measure this distance by using different paths, and then just take infimum over the lengths of all these paths. Infimum of the lengths of all these paths. Okay. So this is the Euclidean distance, and this is the okay. So rho PQ, the intrinsic distance, and this one Euclidean distance in R3. Okay, all right. Well, let's see what's an isometry definition. An isometry, let's say F from a surface to another surface M bar of surfaces in R3 is a bijection, so one-to-one and onto map bijection. Uh, uh, okay, let me write. Is a one-to-one one and onto smooth mapping, mapping, so that its derivatives, its derivative preserves the uh, inner product on tangent spaces for all VW at, let's say, P of M and P in M. So what does this tells us is the following. Suppose this is the surface M and here is our F and this is the surface M bar. It's a one-to-one and onto map. Let's say this is the point P, this is the point F of P, and it does the following. If you send two vectors V and W to, let's say, two vectors like this, okay, say like this. So this is F star V and F star W, tangent vectors, then the inner product of these two vectors is the same as the inner product of these two vectors. And this happens for all vectors and at all points. Okay, so that's the definition of being an isometry. You may think that isometry should preserve the actually distances, and actually that is the uh, next result. So theorem: isometries preserve intrinsic distance, uh, which means what? If F is an isometry from M to M bar, is an isometry, then rho PQ is the same as rho bar of F of P, F of Q. So say rho is the intrinsic distance function on M, and rho bar is the intrinsic distance function on M bar, then F preserves the norm. Distance between 2 points on the surface is the same as the distance of the image points on the surface M bar. And proof is simple because we measure distance by the lengths of curves, and lengths of curves basically integral of uh, tangent vector of the curve joining P to Q. And since Isometries preserves inner product, the lengths of tangent vectors are preserved. So that's the proof. Let's see the details. If alpha is a smooth curve in M with, let's say, alpha A is equal to P and alpha B is equal to Q, uh, with, uh, okay, then length of alpha is what? It is integral from A to B, alpha prime t dt. Well, but then f of alpha is a curve in M bar because, if you have a curve here, let's say, okay, let's say, P to Q, and this is alpha, then f of alpha is a curve from f of P to f of Q, okay? With f of alpha at A is f of P, f of, okay, alpha A, which is f of P, and f alpha at B is f of uh, alpha B, which is f of Q. So it joins this point to this point, and and its length is how much? Let's see, and length of f alpha is just integral from A to B derivative of f alpha t, so t derivative of this, okay, and then you take norm and then square. But our inner product is length preserving, right? It preserves the inner product, therefore it preserves a length of vectors. So this length is the same as the length of uh, alpha. Well, okay, this is f prime alpha t, uh, uh, yeah, okay. uh, okay, so this is f prime alpha prime t dt, but f prime preserves the length, so this is alpha prime t dt, and this is just L of alpha. So this means what? Length of this curve is equal to length of alpha, and this is for all alpha in M joining P to Q. Well, then of course this number, whatever it is, well, this is larger than rho PQ. Why is that? Because this is just one curve joining P to Q alpha, and this is the minimum of all these numbers. So this number is inside the set over which we take the minimum, infimum. Therefore, this is larger than or equal to this one. But then, for any, so we have this gadget here. Okay. Uh, Yes. Maybe I should have done it the other way around. Okay, let me do it this way. Uh, Rho of PQ, no. Then I have this L alpha, which is L of F alpha, and this is just one of the curves joining f of p to f of q. Therefore, it is larger than f of p, the intrinsic distance between f of p and f of q. Okay. Yes. However, alpha was any curve. So for any curve, so this is for all alpha in M joining P to Q. So the set of all lengths over which I will take infimum, every member of that set is larger than this number. So this is an lower bound for that set. Therefore, its minimum, its infimum is still larger than this. Hence, by the definition of infimum, rho PQ, which is the infimum of you know all such uh, lengths, is larger than this gadget. Okay, so this length is larger than this length. However, you know, F is a bijection, is a one-to-one, is a bijection, smooth bijection, is a smooth bijection preserving distances with uh, F star uh, an isomorphism at all points because the derivative map preserves distances, so it cannot have a non-trivial kernel. So it's an isomorphism. But this means that f is a local diffeomorphism at all points. However, we know that f is a bijection, therefore f must be a diffeomorphism at all points. So uh, uh, hence, by the inverse function theorem, f is a diffeomorphism. So so that we have we have a smooth bijection f inverse from uh, m bar to m, inverse of f. Since f preserves distances, its inverse also preserves its distances. Uh, since f is an isometry, so is f inverse, right? Hence, hence by the above paragraph, the distance, right? If there's a smooth bijection from M to M bar, then we have this. Now we have a smooth bijection from M bar to M, then we have the other direction. By the above paragraph, we have F bar, P bar, Q bar is larger than or equal to F inverse of P bar, F inverse of Q bar. This is true for all P bar, Q bar in M bar. Now take P bar to be F of P and Q bar to be F of Q. Then we get what? Then we get rho bar of F of P, F of Q is larger than or equal to rho of F inverse of P bar, which is just P, F inverse of F Q bar, which is just Q. So we see that this is larger than or equal to this, hence these two distances are the same. Okay, and this finishes the proof. Okay. So that's an isometry. So, and isometries preserves distances. They preserve inner products and therefore they preserve distances. All right. Now we have another definition. Local isometry. A local isometry F from M to N of surfaces is a mapping. So it doesn't have to be one-to-one or onto. That preserves dot products of tangent vectors. Okay. It preserves this. So this inner product, sorry, is the same as this inner product. So it is like a isometry, but it doesn't have to be a one-to-one onto map. It doesn't have to be a bijection. However, we do have the following remark. If F M to N is a local isometry, then of course F star is an isomorphism since it preserves the inner product, is an isomorphism at all points of M, and thus by the inverse function theorem F is a local diffeomorphism. At all points. So at every point of M, there is a neighborhood. So it's like the following. Okay, we will see examples. Suppose we have this a plane M and F. Suppose F rolls this plane around the cylinder. We will see that this is a local diffeomorphism, but it's not one-to-one. Okay, so if you choose, for example, a curve like this, okay, its image is probably cover the whole thing. So let's say PQ. So f of p might be equal to f of q. So it is not one-to-one, but it preserves dot products, and this tells us the following. Actually, for every point, there is a small neighborhood here, and let's say, okay, here, uh, and f of p is equal to, and on this neighborhood, f is a diffeomorphism. This is, of course, a consequence of the inverse function theorem. Since the derivative map is an isomorphism, f is a local diffeomorphism. Okay. Here is a fact which we will need. Let f m to n be any smooth mapping. For each uh, surface patch x from d to m, consider the composite mapping x bar, which is just f composition x from d into n, right? So x goes from d to m, and f goes from m to n. So this composition goes from d to n. Consider this mapping. Then f is a local isometry if and only if for each surface patch x we have e equals e bar, f equals f bar, and g equals g bar. Okay, so e, f, and g are the uh, elements we obtained from the surface patch x, length of the vectors and inner products of vectors, and e bar, f bar, g bar are uh, analogous terms on the n surface n obtained via the surface patch x bar, which is the composition of f and x. Okay, here I should point out that here x bar need not to be a surface patch. Why is that? Because f doesn't have to be one-to-one, therefore x bar doesn't have to be one-to-one, therefore it doesn't have to be a surface patch. But still, it preserves, I mean, it gives a parameterization of the surface. Well, it may give a parameterization, yeah. If it is a isometry, then it will. Okay, let's see the proof. All right, now x bar uv is just f of x of uv, and thus uh, x bar u is just f star xu, and x bar v is just f star xv by the chain rule. So if f is an isometry, local isometry, right? Local isometry. Then it preserves inner product. Then uh, E bar, which is just x sub u bar dot x sub u bar, but this is just f star of xu dot product of f star of xu. However, f preserves inner product, therefore this is x sub u bar x sub u, and this is e. F bar is just x sub u bar dot x sub v bar, but this is f star of x sub u dot product f star of x sub v, and this is x sub u dot x sub v, and this is v f. And finally, g bar, which is just x sub v bar dot x sub v bar, and this is f star of x sub v dot product f star of x sub v, and this is x sub v dot x sub v, which is g. So one direction is proved. For the other direction, uh, conversely, conversely, okay, for the other direction, let me write it this way. For the other direction, for the other direction, let's assume E equals E bar, F equals F bar, and G equals G bar at all points. Okay. Then now if okay, W1 and W2 are two vectors on at the tangent space to M at the point P, then I know that W1 can be written like this: A1 times x sub u, and then B1 times x sub v, and W2 is just A2 x sub u plus B2 x sub v for some AI BI, because uh, TPM is spanned by these vectors x sub u and x sub v. Okay, well then now uh, f star of W1. I want to show that f star preserves distance. So let's look at this. We will show that this distance, this inner product is just equal W1 inner product W2. And how can we show this? Well, this is f star. Instead of W1, I write this. Inner product f star A2 x sub u B2 x sub v. However, uh, f is a linear map, so I can write it this way. This is just a1 times f star x sub u plus b1 times f star x sub v. Dot product a2 times f star x sub u plus b2 times f star x sub v. And then uh, by just opening this parenthesis, we get what? This is just a1, a2, uh, f star x sub u dot product f star x sub u, and then a1 b2 plus a2 b1 f star x sub u dot product f star x sub v, and finally b1 b2 f star x sub v dot product f star x sub v. However, we assume that okay, so this is just okay, a1 a2, this is just e bar, and this is a1 b1. Okay, maybe I write it this way. Okay, now let me say, okay, this is uh, uh, well, this is a surface patch for the second surface, and this is derivative with respect to the first vector. So this is e bar, but I know that this is equal to e. Similarly, this is f bar, but this is equal to f, and this is g bar, but that is equal to g. So what we see is then that uh, instead of this, I can just write x sub u dot x sub u, because f, e bar and e are the same, and similarly this is a1 b1 plus no a1 b2, sorry, plus a2 b1 x sub u x sub v plus b1 b2 x sub v dot x sub v. But this is just a1 x sub u plus b1 x sub v. Dot product a2 x sub u plus b2 x sub v, which is just w1 dot w2. So f star w1 times f star w2 inner product is equal to w1 inner product w2. It follows that f is a local isometry. Okay. Well, here is two examples. Let me see if I have time. Okay, I don't have time. Let me stop here. Next time I'll remind you these definitions and do two examples. Uh, See you then. Take care.